we have learned about the various sources, various sources within our body that produce the biosignals. Okay, so, but now we have learned the physiological phenomena as well related to each of these source. Now, what are the biosignals being generated? So we will be learning from in this subsection of the chapter. Okay. So from the previous subsection, from the previous section of the chapter, we have concluded this part, that the sensor that is attached to the body, or some sensor inject the signal into the body and then capture the scattered or absorbed signal, then resulting in recorded biosignal. Examples include, for example, phonocardiogram. This is from the sound of the heart. Electrocardiogram. This is the captured electrical activity of the heart. Mechanospirogram. This is the captured mechanical activity of the lung. Mechanospirogram, MSG. Based on that, then we can derive further using signal processing the physiological parameters related to this biosignal. For example, the heart rate from the ECG or SPCG or SECG, we can derive the heart rate. From the mechanospirogram, we can derive the respiratory rate, FR. Then from ECG and the blood pressure signal, we can also obtain, and the distance measure the blood pulsatil signal, we can obtain the blood pressure. We can calculate the blood pressure. So here, biosignals reflects the physiological parameters. Okay, all these different physiological parameters are embedded within the recorded biosignal. So using the signal processing, then we can derive this different physiological parameter in that recorded biosignal. So diagnostic and therapeutic interpretation. There are mutual interdependencies between the biosignal parameters and the physiological parameters interpreted from that. All of them require the use of sensor attached or implanted or worn, or using sometimes not attached, but using a kind of wave, electromagnetic wave, as the probe, to capture the biosignal. So the objective here is to understand numerous biosignal of this section, numerous biosignal generated in the body and the corresponding related physiological phenomena, and to know how these various physical and biochemical signals were obtained and measured. So here we will explain some of the fetal phenomena and their parameters and the behavior of these parameters. Fetal phenomena is related with the signal coming from the heart, the circulatory system, and the respiratory system. So this relates fetal sign. The fetal sign indicates whether a person is alive or not. The heart is the motor for the circulatory system, as we have learned from the previous section. It pumps blood through the systemic and pulmonary circulation loops. We have learned also from the previous section in the circulatory system section. The heart will receive blood from the pulmonary as well as the systemic veins, and then pumps the blood into the systemic and pulmonary arteries respectively. So the heart is a muscular organ whose rhythmic contraction force blood to circulate within both the circulation loop, systemic and pulmonary loops. Therefore, the heart represents a major source of numerous biosignals, as we have also learned. What are these major sources? What are these numerous biosignals that are related with the heart? Among them, there are the heartbeat itself. This is a biosignal, the important biosignal. If the heart doesn't beat, we know that the person is dead. Then respiration also. This is also related with the heart work. Blood circulation. The blood oxygenation. This is also related with the heart works. And then the body temperature. So for example, here the heartbeat by there are three widely used methods to register cardiac activity. Okay, so this is which are the ECG, the electrocardiography. Then this is the OPG. OPG is optoplethysmogram. Yeah. Then the PCG, phonocardiogram. The ECG measures the electrical activity of the heart. Yeah, electrical activity of the heart, which is usually in clinical setup, we put the electrodes in the heart as well as in the hands and the legs. Okay. Optoplethysmogram is put usually at the end of the fingers to represent the farthest limb away from the heart. Then phonocardiogram measure the sound, the acoustical signal, bioacoustical signal originated from the heart. Yeah, that is why then usually the sound sensor on the microphone is located near the heart, on the heart. So these are the time. This tree graph represents the three different methods used to obtain the heartbeat fetal phenomena. The three biosignals, the ECG biosignals, the OPG, optoplethysmogram biosignals, and the phonocardiogram biosignals. The x-axis is the t of the time, yeah, in seconds for the three different biosignals. So in the first graph, the heartbeat is given from or is derived from the electrical biosignal electrocardiogram, yeah, with lead from the left and right leg, indicating the R peak here. Okay, so from the R peak, when you can obtain this R peak duration, time duration between the R peaks using either electronic, or if this is already digitalized, the digitized signal in the form of digital signal, you can also obtain using programming, yeah, using soft programming software to derive where this occurs, and then based on that, we are using 1 over FC formula. You can obtain this is the time duration, yeah, to obtain the heartbeat, the frequency of the beating, how many beats per minute. You derive it using 1 over this time duration. Yeah. So the B is indicating optical biosignal, optoplethysmograph, OPG, from the finger, yeah, with the advanced version by 160 millisecond, and indicating the systolic diastolic detection, the SSD here. Okay. the length between the systolic here and the diastolic measure. So the distance between two diastolic valley or between two systolic peak indicate that 1 over FC, yeah, the inverse of the heartbeat. Then finally, you can use also acoustical biosignal from the phonocardiogram, ECG, from the heart region near the chest, yeah, with the indicated heart rate FC. So from this, the distance between the first sound. So this is because the heart beats 2 times, yeah, in dub dub, something like that, right? From the heart, yeah, coming from the first one is the contraction, pumping the hearts to the two circulatory systems, and the relaxation. So this is represented by the first sound and the second sound. So if you want to measure the heartbeat distance, heartbeat rate, this is between these two, and between the first sound, or alternatively, we can also measure between the second sound. Okay, the distance. So this is 1 over FC. This is 1 over FC. Okay, so these two represents the time delay from the heart, from the reference of the heart. The optical signal SOPG has a delay due to the length distance between the heart and the finger. Yeah, here, because of there is a distance, actually the dashed line here represents the actual systolic near the heart. But then what is being measured at the finger is this the solid line. Okay, with an assumed wave propagation velocity here of 5 meters per second. If we compare the electrocardiogram and the phonocardiogram, the first hard sound corresponds to the R peaks. Here, the first sound, if we go here, if we draw a straight line, yeah, right, this just here, yeah, just when the R peaks starts. Here, this is similar, so this is the R sound, yeah, near the Q, between the Q and R. Okay, so the first hard sound corresponds to the R peaks. From physiological point of view, it confirms that the atrioventricular valves close, yeah, the valves between the atria and the ventricle, close at the onset of the ventricular systole. Ventricular systole is when the ventricle just begins to pump the blood, the right ventricles towards the systemic, towards the pulmonary circulation, the left ventricles towards the systemic circulatory system. The second heart occurs at the end of the T wave. So T wave is the relaxation wave. Yeah, P, Q, R, S, T. The T wave is here, somewhere here, right? So the second sound here is during the relaxation of the ventricles. Here, this is the second sound. We draw somewhere here. So this is the peak of the T wave, yeah, the PQRST, the T wave, when the electrical charges is already spread towards all the Purkinje fibers, through all the ventricles, and then the two ventricles starts to relax again. So that is the end of the ventricular systole, yeah, when the semiluminar valves close. The semiluminar valves are the valve between the ventricle and the circulatory system. Okay, that is, so when it starts to close, so when all the blood in the ventricles are already pumped towards two circulatory system, the pulmonary and the systemic circulatory, then the semiluminary valve starts to close. This is the T wave. Okay. So when we compare ECG and the OPG, ECG and the optoplethysmogram, the R peaks initiates a steep increase in the light absorption or local blood volume. And here we see again between A and B, the R peak here starts this one. We see this advanced one, yeah, the dash line, because this is what actually happens in the heart. Well, this one is what is being measured in the finger because of the distance. So we make it advanced a little bit, pushing it at some time in advance. So the R peak occurs at this onset of this systolic peak. Yeah. R peaks initiate a steep increase in the light absorption, in this light absorption, namely the onset of the ventricular systole initiates the ejection of blood pulse out of the heart. And when the blood pulse is coming out of the heart, blood flowing into the vessel system here, containing rich oxygen blood, yeah, and this oxygen absorbs the red wave line in the optoplethysmograph. This is what is measured here as the peak in absorption. Okay. Then when we compare the phonocardiogram versus the optoplethysmogram, so here between B and C, yeah, this also the first sound when it is in the systole, ventricular systole, happens almost at the same time with the steep increase in the blood absorption, in the red wavelength absorption by the blood. The second heart sound coincide with the dichrotic notches. Yeah, so the second heart sound will be here. Yeah, here coincide with this notch. Yeah, please look at the dash line. Yeah, the dash line waveline, the advanced waveform, because that represents what happens in the heart. Because if we look on the solid line, this is what happens at the finger, yeah, because of the delay. Then, so this necrotic notch occurs exactly during the second sound. So that is when during the T wave or when the semiluminar valves close, when the ventricle starts to relax. Yeah. So when P aorta is larger than the P of the left ventricle, the valve closes. Coincide with the consecutive closures of the semiluminar valve or the aortic valve. The valve between the vessel, the ventricles, and the circulatory system, the systemic circulatory system. Okay, so far, is it understandable by that what occurs here in these three signals? So by
Sir,
yeah,
I want to ask, what is T wave?
P wave is, remember the previous chapter, yeah, on the previous section on the heart. The T wave is the so this is P, this is P, Q, R, S, T wave. This is T, QRST. Yeah, usually in ECG electrocardiogram, we represents the ECG as PQRST. R is the peak here where ventricle systole occurs. If you could please review the previous lecture, yeah, the recording video is there, and the slide also, the previous slide, not this slide, where we describe about the physiology of the heart, the electrical activity of the heart. So when the T wave occurs when all this charge already flowing, yeah, from his bundle, to the Purkinje fibers in the two ventricles, two branches of the ventricle, and then spreading throughout the ventricles. Then all the pumping is occurs already from the ventricles towards the systemic circulatory system and the pulmonary circulatory system. Then the valve starts to close, the ventricle starts to relax. That is the T wave, when the T wave occurs. Okay, from the ECG perspective. From the ECG perspective, and we know that this ECG is related with the mechanical activity of the heart. Okay, so that is what I can explain from this slide. Yeah, if I don't want this slide to come back to the previous slide, because it is in different file. So please review the previous lecture and the previous slide. Is this also there? The T wave is explained there.
Okay, sir, thank you.
So you see that from these three different biosignals, the ECG electrocardiogram, OPG optoplethysmogram, and PCG phonocardiogram. And by comparing these three, we can obtain various information related to the what actual physiological phenomena occur, yeah, during the different position within these three waveforms. Yeah, this is the electrical waveform from ECG. This is optical waveform from optical biosignal from the optoplethysmograph, and this is bioacoustical signal from the phonocardiogram. But all these three biosignals originate from the heart. Yeah, see, we see that is why the heart is a major source of numerous biosignals. The more you can have at the same time, of course, then the more it is easier to diagnose the condition of the patient. Unfortunately, of course, these three sensors are not widely yet available at the level of front-end clinics, yeah, because maybe the price is not that cheap. Yeah. With the current, actually, technologically it should be made lower cost, but somehow it is not yet widely available. Okay, so other methods that can be used to measure the biosignals, the heartbeat, yeah, from the heart, among others, is the electroplethysmogram, EPG. This is an electric biosignal based on detection of pulsatory changes of the electrical tissue impedance. Yeah, so related There is also electrical signal related to the pulse of the heart pulse that can be measured from the tissue impedance. The tissue impedance also will change when the heart is beating. Magnetocardiogram. This is, I think, explained by one of the group that time, I think 2 weeks ago. Maybe. A magnetic biosignal gives magnetic fields emitted by the electrical heart muscle excitation. Barocardiogram. This is mechanical biosignal reflecting the periodic changes of the blood pressure. Mechanocardiogram, MCG. This is mechanical biosignal found through local skin deformation and vibration. Yeah, because of the pulsating blood vessel. So we can put a strain gauge, for example, underneath, yeah, on the near the heart to measure this mechanocardiogram. So another mechanocardiogram showing pulsatory changes in the volume of the capillary bed. This is larger finger volume can be observed during blood ejection and a smaller volume during diastole. So this one measure only the volume changes, while this one measure the skin deformation and vibration due to the pulsating blood vessels underneath. So if you put the sensor on big blood vessel, you can measure both the finger volume expansion and contraction as well as the vibration due to the pulsating blood vessels. Then ballistocardiogram (BCG). This is also mechanical biosignal based on the recording of accelerated mass movement. It is the mass of both the heart and the circulating blood imparted to the body with each atrial or ventricular contraction and forced blood ejection. So when we are beating, our heart is beating, basically like the heart is creates a pressure, right? It's like punching or impacting the surrounding tissue of the body. So this can be recorded as well, yeah, as the acceleration of this mass surrounding blood, and then it relates with the heartbeat. This is called as ballistocardiogram, the overall beating. And the mechanocardiogram in the previous one, more of local blood vessel. Yeah. There is also less direct method. Yeah, this is direct method which measure directly the signal coming near the heart or from the blood vessel. In less direct method, we use some waveform to measure the heartbeat. So ultrasound Doppler using ultrasound signal, which is basically acoustical signal, reflects with high frequency. Yeah. It will be reflected, yeah, by the pulsatil blood velocity within the large vessel. Yeah, using the Doppler phenomena, Doppler law. We can use also, instead of acoustical signal, we can use optical signal, what we call as laser Doppler. We use a laser in combination with interferometric methods to quantify minute skin displacement because of the pulsating blood. Yeah, of course, this is more sensitive, yeah, compared to acoustical signal, but maybe then the scope, the spatial volume will be very small, and sometimes it is too sensitive that it may capture also other interference signal. Instead of acoustical or optical, we can also use other form of electromagnetic wave in the radio wavelength. And then we can use microwave Doppler radar technology that measures cardiac displacement of the chest region with respect to an ambient antenna. So here we can measure the heart using a sensor which is basically located in the not contacting it. Ultrasound, usually the transducer still needs to be contacted with the body in order that the acoustical signal from the transducer can travel through the body without any hindrance. Laser Doppler, although it could be also without contact, but normally to make the signal clear, to have a high signal to noise ratio, it should not be put to big too far distance from the skin. But microwave Doppler radar technology is more non-invasive, so it can be put a little bit far, yeah, and then generating microwave like a radar from here. Then some part of it will be reflected, yeah, by the heart. We can use also high-resolution thermal imaging of superficial blood vessel, yielding pulsatile blood flow. And this is because the blood vessel will normally have different temperature compared to the surrounding tissue. And using high-resolution thermal imaging, then uh, we can observe the pulsatile blood flow. So the heartbeat phenomena itself, yeah. Each biosignals in this what is has been described in the previous slides, yeah, the phonocardiogram, electrocardiogram, optoplatismogram, mechanocardiogram, ballistocardiogram, magnetocardiogram, etc., shows a unique waveform, yeah, and behavior for normal and pathologic cardiac cases. So the formation methods of these respective biosignals, the interface between the physiological mechanism that form that biosignals and the registered biosignals, there's two here, the physiological mechanism that form that biosignal, for example, the heart beating, and the registered biosignal, ECG, BCG, or OPG, MCG, etc. The relationship between them, the interface between them, the connection between them, this is very important. Pulsatile blood pressure, blood flow, and blood velocity in vessels are this interface example. So the initiation of heartbeat here is described by the instantaneous FC, the frequency of the beating. The level of FC and its change are largely under the control of the autonomic nervous system. Yeah, it means involuntary system, yeah, which we are not conscious of. This is mediated via the sinoatrial node, yeah, the node, the node in the upper end of the heart, which function as the main pacemaker of the heart. So the balance of efferent, sympathetic, and parasympathetic activities will determine the instantaneous heartbeat frequency, yeah, modulated via the central oscillator in the central nervous system, as well as the peripheral oscillators. The level of the frequency of the heartbeat provides one of the most efficient measures of estimating energy expenditure. So this is some way from that heartbeat phenomena, one phenomena, heartbeat FC, we can then estimate other physiological phenomena, like the energy, in this case, energy expenditure. For example, when we need more oxygen, then our heart usually will beat faster. Okay, so when we are climbing a mountain, yeah, we start to experience hypoxia, then our heart will beat faster. So this is related with this energy expenditure. Or when we are exercising, also we need more oxygen, yeah, to generate energy in our body tissue. This will also increase FC, yeah, our heartbeat. So the heart period, yeah, which is equals to 1 over FC, the inverse of FC, usually refer to the RR interval. So this is the interval between the R wave peak, the R peak, the time interval between two consecutive R peaks of the electrocardiogram, the ECG. Consider limitation of the RR interval to assess the activity of the sinoatrial node. Then another heartbeat phenomena signal which we can measure besides the what do you call it, heartbeat, is the heart rate variability, the HRV. So this has become a standard term to describe both the oscillation in the heart period, heart rate variability, yeah, the oscillation of the period of the heartbeat, as well as the oscillation between consecutive instantaneous values of FC, although this definition is less common. More, it is used HRV as to define the oscillation in the heart period. Yeah, the heart rate, the R, how the the distance between R and R peak, the RR peak changes with time. So this is called the HRV. So here, the RR peak changes, yeah, with time. The specific behavior of the interbeat interval, which is called as the rhythmograms during the different sleep phases. Rhythmograms, it can be observed that the most obvious phenomenon in the rhythmograms is the interval modulation with the respiration, as discussed later. This one. Okay, so yeah, this figure shows the rhythmograms, yeah? The specific behavior of interbeat intervals, right? So for example, here shows the RR peak when the person is awake, and then this is the during the first NREM, yeah, the non-rapid eye movement, so the deep sleep. Then this is another non-rapid eye movement. Afterwards, during the rapid eye, the paradoxical sleep, the rapid eye movement number 4. Yeah, so taken with the RR equals to 1 over FC, the variation of the heartbeat, yeah, or heart rate variability over time T as derived from R peaks of electrocardiogram during the different awake and sleep phases. This is and B here, this is the corresponding somnogram. Somno represents the recording during the sleeping, yeah, of the subject, showing successive awake and sleep phases and stages. Okay, so this is the during the awake phase, the HRV average, yeah, then during the REM, going down here, going to the deep sleep. First, deep sleep 2 second, deep sleep third, then deep sleep 4, going back to deep sleep 2, etc. Yeah. So this is varying average of the rhythmic, yeah, HRV during the person's sleep period. So this is showing the minute time in minute. Yeah, so in 350 minutes, so means about 6 hours of the sleeping of the person until that person awake again. Okay, so that by measuring the HRV, heart rate variability, we can also indicate the states of the person awakeness, yeah, or person sleep. So the most important requirement for a reliable HRV analysis are summarized below. So the sampling rate of the biosignal should be relatively high, larger than 500 Hertz for a precise estimation of the instantaneous FC, the instantaneous heart rate. Okay, it is significantly higher if you use during the standard electrocardiogram recording, which is usually in 256 Hertz, sometimes even lower. Okay, then the next vital phenomena is respiration, coming from the lung and the respiratory system. So the lung is responsible for delivering oxygen into the bloodstream, as well as the release of carbon dioxide from the blood, yeah, through its rhythmic expansion and contraction. An assessment of the resulting respiratory cycle with the respiratory rate FR, yeah, this is the respiratory rate, and this is a vital issue from a diagnostic and therapeutic point of view. And numerous biosignal can register this FR. So similar with FC, we can also register FC, the heartbeat, using ECG, PCG, OPG, BCG, MCG, etc. FR can also be registered using different types of biosignal. Okay. So for example, here we can use this MRG, PCG as well, and MSG. Yeah. What are they? MRG is a mechanorespiratograph. Mechanorespiratograph. Yeah, by uh, putting two sensors at the chest, mechanical sensors. One is at the chest, and the other one is at the abdomen, here, at the stomach. Okay, so here the abdomen is shown in the dashed line signal, while the chest part is shown in the solid line signal. Yeah, so when the person is asked to hold the breath, for example, to simulate apnea, this is what occurs. Okay, that it's just flat, and no cycle happens. So then this is during the inspiration and expiration. Yeah, I think this is during the inspiration, but the peak increases. This is during the expiration. Okay, so this is relative unit showing the expansion and contraction of volume of both chest and the abdomen. And this is during the provoked snoring. So the FR, the respiratory rate, can be derived from the distance within two peaks, yeah, of this inspiration, or between two valleys of the expiration. And the inverse of that will be the FR. It can also be derived from the PCG, phonocardiogram signal, yeah, the acoustical phonocardiogram, but of course, sometimes they are noisy because the sound from the heart mixed with the sound from the lung. Yeah, so here is the heart sound, but the distance of which the envelope, the peak of the envelope represents the respiratory sound. So here we can see from this peak during the inspiration, this is the peak. This is when it is holding breath, it is relatively flat, the envelope. When it starts to have cycle again, respiratory cycle, then the peak of the sound also here varying. Okay, this represents the inspiration, and so we can measure the distance between two envelope peaks here, and then obtain the respiratory rate. Then the C part is when we use mechanical biosignal mechanospirogram. Yeah, from the mouth airflow, MSG mechanospirogram. So this is mechanorespirogram, immediately measure from the chest. And this one is mechanospirogram, from the mouth airflow coming from the mouth. So here we can put some sensor in front of the mouth, like for example in the form of mask. Then this can measure the inspiration and then respiration, the inspiration and expression step in during the respiration. And this is during the snoring. When the person is snoring, it shows larger peak or larger valley here, deeper valley, and with some vibration, yeah, in the peaks or oscillation. So the mechanorespirogram is mechanical biosignal resulting from the circumference change, yeah, the volume change of the abdomen and the chest during the breathing. So from here we can obtain periodic waveform where FR can be observed during normal breathing and disappears when we hold breath. So if you compare the chest and the abdomen biosignal, they have different amplitudes. Yeah. This is due to the different strengths between the abdominal and chest breathing. But the amplitude, not only the amplitude, but the phase of the latter biosignal may differ of the chest breathing. For example, here there is a phase difference between the chest and the abdomen. This is due because the two are being asynchronous, not at the same time they expand together. But most of the time, the chest may be expanding first, yeah, like this. The chest is expanding first, or contracting first, and then followed by the abdomen. Okay. This is what it means with asynchronous. In the SPCG or phonocardiogram, this acoustical biosignal mainly visualize the heart sounds arriving from consecutive closure of the heart valve. So that's why mostly the sound that is being heard is the sounds coming from the heart, the higher frequency signal. However, the lung sounds are also present when during the normal breathing due to the air turbulences in the branching, yeah, in the bronchial airways of the lung. These sounds cannot be easily distinguished in time course due to a much lower amplitude. But usually we can observe them as here if we see clearly from the envelope of the signals from the PCG. Then finally the mechanospirogram, MSG. This is mechanical biosignal that reflects the respiration. And this is quite used in clinical practice, yeah, for pulmonary rehabilitation or pulmonary medicine. Yeah, yeah, it specializes in physiology of the lung. It's given by recording of the airflow through the mouth, while the eventual nasal airflow is stopped by clip. So the nose is being closed, so the person only breathes through the mouth to measure this MSG, mechanospirogram. The airflow through the mouth is registered by a mouthpiece connected to an airflow transducer. It basically consists of a tube with a woven screen inside, which acts as the flow resisting object, as a flow resistant. During inspiration, when we inhale, the outer side of the flow resistance has a higher air pressure than the inner side towards the mouth. That is why air flows inside. During the expiration, the reverse is true. So the resulting pressure difference across this flow resistance reflect the non-zero airflow pressure difference and flow resistance. So there are two of this screen, yeah, open screen, inside and outside, and then the difference between the two will determine whether there are airflow or not. The measured pressure difference is converted to a voltage with the amplified and calibrated version being shown in this figure 3.5C, yeah, this part. Okay, so this is already measured the pressure difference between the two pressure, yeah, the two air pressure inside and outside of this transducer, yeah, airflow transducer. This is when we are zooming in into the MRG, mechanorespirogram signal. Yeah. So you see here there is a bit of difference of phase between the chest and the abdomen when we zoom in. And then B is the snoring sound, provoked snoring sound here, and the heart sound in phonocardiogram. Yeah, mostly what we hear is the first heart sound, second heart sound. So it's not that easy to determine the respiratory cycle from here. And the C here showing the zoom in of the flow in MSG, mechanospirogram from the mouth, airflow measurement. Yeah, from here, then we can also have Fs, flow oscillation. Yeah, we did it Fs during the provoked snoring in mechanospirogram with indicated heart rate and respective sensor location. This is the sensor location. When holding a breath, the mechanorespirogram in figure 3.6a discloses a residual cardiac component. Yeah, this is during a holding breath region, yeah, where we hear in this zooming out picture, we only see it as a flat line, but when we zoom in, this is what we see. There is actually some variation due to the heart rate, due to the heart beating. So the distance between these two valleys indicates the heart rate, yeah, the duration, the heart period. This component reflects periodic global vibrations of the chest circumference due to local vibration of the chest wall, which are initiated by mechanical pumping action of the heart. That is, the vibration themselves are imparted to the body with each heartbeat during the heart's ventricular contraction when the blood is forcefully injected into the arteries. The phonocardiogram depicts snoring sounds during the inspiration phase, which overlaps the heart sound. This one. So the heart sound is overlapped and is buried or is hidden within the snoring sound. The airflow oscillation in the mechanospirogram here, where the oscillation rate for the heads of the intermittent airway closures during provoked snoring here can be easily derived. The frequency of the snoring related to here. We can also measure this respiration using thermal signal, what we call as thermal biosignal or thermorespirogram, TRG. Okay, so here we will have also oscillation because either here as this is a mechanical respiratogram measured from the expansion and contraction of the volume of the chest, and this is the thermorespirogram measured from the temperature of the breath out air from the nose. Okay, so when there is air, when it captures the breathing, the air from the coming out from the nose, of course the temperature increases because it brings the body temperature within the body temperature inside. That's why the temperature slightly increases. Indicated, and from there we can indicate the respiratory rate, FR. And the sensor is located just in front of the nose. Other methods that can be used to measure respiratory signals, to measure respiration, are the electroplasmogram, EPG. Yeah, so this is an electric biosignal based on monitoring the thoracic electrical impedances change due to the cyclically inflated and deflated lungs. This is similar to mechanorespirogram. However, it is not measured mechanically. In mechanorespirogram, you measure the expansion and contraction of the volume by you can use strain gauge, for example. But this one using the impedance of the tissue change. So by inductance plethysmography, so using inductance, yeah, when it expands, then the coil inductance, remember electric circuit 2, like in the second semester, is basically based on the coil, what do you call it, the coil number. When the charge expands and contract, this coil number will change, the loop, yeah. And the resulting electrical inductance of the wire is measured. The inductance increase with the area of the loop encloses, and thus with the inspiration phase of the respiratory cycle. We can also measure respiration using optoplethysmogram, using optical biosignal, which will reflect the peripheral blood volume changes over the respiratory cycle. Then we can measure using ECG also, electrocardiogram, which is electric biosignal, which will echo the periodic and mechanic heart displacement due to the varying lung volume in the inner thorax. Of course, it needs another type of signal processing, some signal processing to be able to discriminate the signal coming from the respiration and that one coming from the heart. We can use also flexible pads like piezoelectric foils sensitive to pressure and use it under the abdomen and chest to detect the shift of the subject center of mass during respiration. So these are different ways of measuring respiration. Some detectable physiology that can be measured from the respiration by signal, one like apnea. Yeah, this is one of the disease cause the sleep disease usually. Breathlessness, obstructive sleep apnea (OSA), occlusion of the upper airways. Yeah, here when the upper airways is closed, yeah, and it may yeah, then air cannot be flowing into the trachea. So with maintenance of rhythmic contraction of respiratory pump muscles yielding thoracoabdominal exclusion for at least 10 seconds and a delayed fall in oxyhemoglobin saturation of more than 4%. So you can measure using optoplethysmograph, for example, to measure fall in the oxyhemoglobin saturation. Or otherwise, you can measure using thermorespirogram, yeah, or mechanorespirogram or mechanospirogram to detect the occurrence of OSA, obstructive sleep apnea. Central sleep apnea, temporal failure in breathing rhythm generation due to a lack of neural stimulation, lasting at least 10 seconds. Then mixed sleep apnea, MSA, consists of successive CSA and OSA segment. Initial period of decreased central drive, followed by an obstructive breath. This is the example of how those three different respiration physiology and the apnea, the three different types of apnea can be measured using this various signal. Yeah, so multi-channel monitoring of sleep within the scope of polysomnography. This is indicating the mixed sleep apnea MSA, indicating OSA, obstructive sleep apnea. Yeah. So from top to bottom, this is the airflow, a milliliter per minute. This is measured chest extension. Yeah, so can be measured using mechanorespirogram. Then abdominal extension. This is from the abdomen. This is what the indicative signal during MSA and AOSA. Then sum of the chest and abdominal extension. So this signal represents the sum of this and this, yeah, relative sum. Then this one is blood oxygenation, hemoglobin oxygen saturation. Usually it is measured using optoplethysmogram. And this one is the heart rate variability, the HRV, which can be measured using ECG, MCG, or other methods. So this dash arrow indicate the temporal here, desaturation and drop of the heart rate. Notice the heart rate here drops during OSA. Also here during the OSA, the heart rate drops, which corresponds to the depicted MSA, mixed sleep apnea, and OSA, obstructive sleep apnea. Okay, any questions so far regarding the heart signal and respiratory signal, respiration signal? Then let's see what kind of fetal phenomena of signal from blood circulation. There are three different signal or physiological phenomena that can be registered using biosignal: the blood pressure, the blood flow, and then the arterial radius. So the first blood pressure measurement is done by Stephen Hales in the 17th to 18th century, who is an English physiologist. He pioneered the quantitative measurement of the blood pressure in animals by using a vertical glass tube, one end inserted into the horse artery. The rise of the column of blood in the tube was an estimate for the instantaneous blood pressure level. The methods could be, for the blood pressure measurement, could be invasive and direct method, measuring directly into the blood vessel, or non-invasive and indirect methods, measuring outside the blood vessel. This is, for example, how we can measure blood pressure continuously and unobtrusively. Yeah, this is using mechanical biosignal, barocardiogram, BCG, from the finger in the right hand. Let's see. This is actually the solid line is the measured one. The dashed line is the advanced waveform to simulate the actual blood pressure occurring in the heart. Yeah, because the one that is measured in the finger is basically is already delayed blood pressure because the blood pulse travels from the aorta into the finger. Okay, so this is measured using barocardiogram. Yeah. So the approximate start of the reflective wave, the inflection points here are indicated by arrows on the measured waveform. Here, this one, the inflected part. So which is indicate, and then the dichrotic notch here. So this is systolic, and then this one is the diastolic blood pressure. The PD is the diastolic blood pressure. PS is the systolic blood pressure. And the B is acoustical biosignal from the phonocardiogram, SPCG, from the heart region of the heart. So this is how the blood pressure is corresponding to the sound of the heart. Yeah, so we have the blood pressure, the actual blood pressure near the heart is made by advancing the measured blood pressure from the barocardiogram here with several times corresponding to the first heart sound. And the C here from the electrocardiogram, ECG, measured from the lead 1 Eindhoven with the indicated RPX measured from the two hands. Yeah, lead 1. So here showing the indicated RPX corresponding to the first systolic pressure. Barocardiogram is a mechanical biosignal based on the volume clamp method and represents the T waveform in the radial artery with the corresponding systolic pressure and the diastolic blood pressure. So this exhibits periodic waveform oscillating with fundamental frequency Fc. Yeah, this waveform reveals the primary and secondary peaks within the cardiac cycle. The phonocardiogram represents the heart sound. The electrocardiogram represents the electrical heart signal from the heart muscle excitation. If we want to measure invasively, monitor the blood pressure invasively, and this is actually the most accurate one, because the actual blood pressure inside the vessel, yeah, by inserting catheter with a mounted internal pressure sensor, or by inserting a fluid-filled and rigid catheter for transmitting the blood pressure waveform to an external pressure sensor. So either the pressure sensor can be inside this catheter, yeah, directly inside the catheter, or another way is the pressure sensor is outside, and the blood pressure is transmitted using fluid inside the tubing, yeah, inside the polyurethane tubing, brought to this transducer located outside the body, and then there is where the blood pressure is being measured. And this is two ways of measuring the blood pressure using invasive monitoring. If we want to measure blood pressure non-invasively, the most common one is using auscultatory method, using Korotkoff sounds. This is using sphygmomanometer in conjunction with stethoscope. Okay, the Korotkoff sounds is detected by stethoscope head to determine when the PS and PD occurs. The systolic and diastolic pressure occurs. The inflatable cuff encircles the upper arm, and the cuff pressure is increased until a complete cessation of the blood circulation downstream, the brachial artery, of course, yeah. So it stopped the blood circulation. Then after that, the cuff pressure is released. Then the first coronary cuff sound, release coronary cuff sound will be heard using stethoscope. This is the time instant when the upper systolic part of the blood pressure pulse wave passes under the cuff. And that the pressure during that sound, the first coronary sound, is equals to the PS, the systolic pressure, systolic blood pressure. After that, following the transition from muffling to the silence, heard through the stethoscope, this is the time instant when the lower diastolic part of the pulse wave passes, and the time the cuff pressure will be equals to the diastolic blood pressure. Okay, this requires the use of this cuff, yeah, inflatable cuff. So this is the graph shows the auscultatory method in comparison with the volume climb method for blood pressure monitoring. Yeah, the A is the mechanic biosignal from the barocardiogram from a finger on the right hand. Yeah, yeah, and then the barogram, yeah, from the upper arm of the on the left. Yeah, so the big black line here indicates the barogram, while this one, the sharper one, indicates the optoplatismogram signal. B, this is the acoustical biosignal, the SPG, from the upper arm on the left. So the sensor is located in the upper arm of the left on the left. Like this. This is what we heard, what we will hear. This one, the C indicates electrocardiogram measured using lead 1 Eindhoven, where the two electrodes are located in the two hands. And D is using optical biosignal, optoplatismogram, located in the finger on the left hand. So this happens on the same patient at the same time traverse. So the systolic pressure here occurs like this. If we are using auscultatory method, this occurs the PS here just exactly when if we use stethoscope or phonocardiogram at the brachy, yeah, the vessels here, blood vessel here, just when it starts, the blood starts to flow. Yeah, when there is sound here. Then the diastolic blood pressure is measured when the sound just beginning from this muffling period into silence. Yeah, more or less somewhere here. So this is the measured blood pressure. So the systolic and diastolic is measured during that two period. Yeah, this is when the cuff pressure is start to be released and then blood start to flow, and then you will hear this sound. And this is when it starts to silent again, to be silent again. We can also use non-invasive method, which is called as oscillometric method. This is the successor of ancient mercury as sphygmomanometer, using the principle that pulsatil blood flow produces radial oscillation to the arterial vessel wall, which are transmitted to the cuff encircling an extremity, and thus to a pressure sensor within that cuff. As soon as the intra-arterial blood pressure exceeds the cuff pressure during the deflation, and when the pressure inside the cuff is released, the oscillation of the vessel's wall are strengthened due to a turbulent blood flow and progressing arterial decompression. The cuff pressure at the time of the initial increase in the oscillations amplitude correspond to the systolic pressure, and that during a subsequent rapid decrease in the oscillation correspond to diastolic pressure. In fact, the maximal amplitude of the oscillations of both vessels walls and cuff pressure is observed when the cuff pressure passes the mean arterial pressure. That is when the systolic vessel radius has nearly reached its final value because of the actual decompression, but the diastolic radius is still zero, nearly zero. Another method of non-invasive blood pressure measurement is called volume clamp method or vascular unloading method. This is using miniaturized cuff encircling a finger, for example, that is equipped with an optical transmission sensor, okay, inside that cuff, optoplatismograph, for example. When the radius volume of the finger artery tends to increase during the blood pressure pulse, as detected by the transmitted light intensity, the cuff pressure is also increased just enough to keep the radius and thus the transmural pressure constant. So the resulting cuff pressure waveform compares favorably with the blood pressure waveform. So similar with the blood pressure, because when the blood pressure increase, this cuff will try to increase pressure also to balance it. Because at constant PT, in order to maintain this transmural pressure between within the interface of the radius of the blood vessel and the cuff. At cuff PT, the cuff pressure outside blood vessel follows the intra-arterial pressure up to a constant factor, right, to make it constant. So this is using a active feedback. A pneumatic feedback system is established for cuff pressure volume control, so that the PT, the transmural pressure here, approaches zero, and the pulsatile changes of the vessel radius become maximum. Okay. Okay, this is something parameter. Yeah, unfortunately, I haven't made the slide here yet. About this is also occurs due to the circulatory system, the blood oxygenation. This is inside the how high is the level of oxygen in the SpO2. This is quite important now, yes, with the COVID-19, etc., phenomena of happy hypoxia, etc., to measure the content of oxygen. This is usually measured using optoplatismogram, yeah, that measure the relative intensity between red absorption, red wavelength absorption, and infrared wavelength absorption. Okay. Okay, so there are many other parameters here which is not yet measured, which is not yet explained, but this can be measured using the previous recording, yeah, the interrelation between cardiac and respiratory parameter, between the heart and the systemic circulation parameter. Then from there we can obtain biological rhythm, the sleep parameter behavior, etc. So this is the conclusion similar to previous section basically. So the sensor is important to record that biosignal, and the result of the measurement by the sensor will be is recorded biosignal. And then depending on the phenomena, depending on the position of the sensor, usually what we use is electrical sensor, electrodes, or mechanical sensor, or acoustical sensor. From there, we can measure, depending on the position where we locate the sensor, we can obtain various different types of biosignal. In this case, for phonocardiogram, acoustical sensor that is placed near the heart to measure the sound of the heart. Electrocardiogram, for example, electrode measuring the electrical activity of the heart. Mechanospirogram, mechanical sensor used to measure in the chest and the abdomen to measure the respiration activity of both chest and abdomen from the chest and abdomen expansion. We have mechanospirogram is from the mouth, from the mouth. Mechanorespirogram is from the chest and the abdomen, and we have many others. Mechanocardiogram, measuring the vibration of the skin due to the heart pulse, the heartbeat. What I mean. Ballistocardiogram, measuring also the heartbeat activity from the impact caused by the heart into the body, etc. From all those recorded by signal, then we can, using signal processing, we can interpret them and then obtain the physiological parameters relevant for the physician, the heart rate, respiratory rate, and blood pressure. So this is your role as biomedical engineer. Your role is using the sensor, the correct sensor, or developing the correct sensor for particular measurement, recording the biosignal, and after that also using signal processing, interpreting the biosignal, producing secondary data. We call it as this physiological parameter, heart rate, respiratory rate, blood pressure, and many other, heart rate variability. From there, then the physician can make their diagnostic of their therapy. Some physician may use this their experience to interpret directly from PCG, ECG, MSG, but usually if it is aided with some type of signal processing to obtain the secondary data, the physiological parameter, then it would help the physicians a lot. Yeah, then the physician can do better diagnostic. And this is something which is not yet widely available in all clinics. Many of them are only available in the hospital. Any questions so far?